Okay, so here we are back. This is the second video. You might have already skipped through the limits one, but here's the one for exponential derivatives. In class, I might have showed, I actually showed 6th, I didn't show 7th because of just time. But to do the derivative of exponential functions, we use that logarithmic differentiation. So take the log of both sides, that gives us ln y equals ln b to the x. Okay, that allows me to bring the x to the front. So natural log of y equals x times ln of b. Now you got to remember this is a number here. So when I take the derivative of both sides, I get 1 over y times y prime equals, well, the derivative of x is just going to be 1 times ln b, so it's ln of b. Then multiply both sides by y. And what was y? It was b to the x. So I get y equals ln b times b to the x, which we'll come back to that in a second. But that's the general derivative function for exponential functions. Now e to the x is nice because it's a specific case of this. So I'll do this in a different color. Let's do this in, I don't know, how about a green, like a nice green. I haven't used green before. So again, start off doing the same thing. Natural log of y equals natural log of e to the x. Now we talked about this though. Natural log of e to the x, that x drops down and we get the natural log of e. That guy just gets x. So ln of y equals x. Now take our implicit different derivative of both sides. So we get 1 over y times y prime equals, derivative of x is 1. And then when you multiply both sides by y, y prime actually equals y. So here's a very special property about exponential, about the e to the x. Its derivative equals the original function. Y prime equals e to the x again. So this graph is its own derivative, which is also why it's so special in calculus and why we spend multiple days working with just this exponential function, basically. Okay, so our two derivative rules. Okay, d dx of b to the x is ln b times b to the x. The more important one, though, e to the x is e to the x. Okay, so those are our two differentiation rules for general exponential function, specific e to the x exponential function. It's its own derivative. This guy, ln b times b to the x. So here we go. First derivative, y equals e to the tangent x. Well, y prime is going to be the derivative of the, and again, this is what we got to remember, this is a chain. This is really e to the x, or more importantly, e to the f of x. And when you do the derivative of that, it's going to be the base stays the same, so e to the f of x, but times the derivative of the exponent, f prime of x. So in this case, e to the tangent x is going to be e to the tangent x still, but times the derivative of tangent, which is secant squared x. That's it. Okay. If this would have been, let's say, for just sake of argument, y equals 3 to the tangent of x, okay, dy dx would have been natural log of 3 times 3 to the tangent x times secant squared x. Okay, so I would have had to do natural log of the base, which is natural log of 3, times b to the x, which in this case would be 3 to the tangent x, because again, it's the original function. But then that chain rule means I got to multiply by secant squared. Again, AP doesn't seem to focus on this too much, and a lot of calc books kind of leave it out, but it is something you should at least see. All right, next one, next derivative. Okay, find y prime if y equals e to the negative 4 y equals e to the negative 4x times sine of 5x. So we have here for us a product rule. So dy dx is going to be derivative of the first, which is e to the negative 4x times the exponent, which is negative 4, times sine of 5x, plus, first leave it alone, times the derivative of the second, which is cosine of 5x, times the derivative of the inside, which is 5. And then we'll just clean this guy up. Negative 4e to the negative 4x times sine of 5x plus 5e to the negative 4x cosine of 5x. And there we go. Okay. Next style of example for this guy. Find the absolute maximum value of f of x equals e to the negative x. So what this means is first derivative, check out our max and mins. So first derivative of this guy is going to be a product rule because it's x times e to the negative x. So the derivative of the first is 1 times e to the negative x plus the first times the derivative of the second. Well, that's e to the negative x times negative 1 because that's the derivative of e to the negative x, or negative x. Let me clean this up a little bit. E to the negative x minus x e to the negative x. We want it to equal 0. So what I'm going to do is take out e to the negative x, and I get 1 minus x. And the question becomes then, can either of these equal 0? So if I said e to the negative x equal to 0, and 1 minus x equal to 0, I get x is 1 here. That's pretty obvious. This guy, though, this is really 1 over e to the x, and can that equal 0? No. Okay. Now, I could if I let x equals, so no, so I can't even mess with this. So there's no max or min from this guy. Maybe a point of concavity later, but this is only asking for absolute maximum, which in this case we know it's a maximum. It's got to be x equals 1. But let's test that. We'll do 1 for our number to check for concav, or for max, we get 0. If I plug a number less than 0 in, like say negative 5, okay, like negative 5, that's going to be e to the opposite of negative 5, which is really positive. Okay, and then it'll be 1 minus negative 5, which is really plus. So I'm going to have e to the 5th power times 6. That's positive. Okay, if I plug in a number bigger than 1, like let's say 10, that'd be e to the negative 10th times 1 minus 10, what's negative 9. So this number is still positive. It's just 1 over e to the 10th, but times the negative 9, it's a negative. So this has to be then the absolute maximum. Now, what's the maximum value, though? So that means I have to go back to this function and plug in f of 1. 1 times e to the negative 1, that's really just 1 over e. So there's our maximum value. It's at x equals 1, 1 over e. And if you really wanted to look for it, you could just take a look at the graph and the graphing calculator and see that, yep, there's a max there. Actually, I'll just do that real quick. Maybe give you a chance to catch up to what's going on. So x e to the negative x. There we go. There's the graph. It goes up at 1 over e. It ends up leveling out and going down there. So yeah, I'll do e comma f of, so it's 1 comma f of 1. There we go. There's the maximum value right there. And 1 over e is actually 0.37. All right. Next example. Okay. This one is an implicit differentiation. So we had to find y prime. I know it's implicit differentiation because I've got y's on both sides and I can't get them together somehow. So do the derivative of this guy. Actually, let's see here. Yeah, do the derivative of this side. So I'm going to get e of x over y times the derivative of x over y. Now that's going to be a little ugly, isn't it? It's going to be a quotient rule, or we could just do this. X times y to the negative 1. That ends up being 1 times y to the negative 1 plus x times negative 1 y to the negative 2 times y prime. So 1 over y plus, minus x over y squared times y prime. Derivative of x is 1. This guy is then minus y prime. So, that is just ugly. So e to the x over y, over y, if I distribute that in, minus e to the x over y times x over y squared times y prime equals 1 minus y prime. Got to move this term over here by adding it. Got to move this one over here. So we get e to the x over y minus 1 equals e to the x over y x over y squared times y prime minus y prime. Now I have to factor out the y prime here, so I'm just going to, this will really be a 1 y prime. And oh man, that is just ugly, ugly, ugly. Yeah. Wow. I wanted to look at an implicit differentiation problem, but I didn't realize this was so bad. Well, now we got to divide by all of this mess. So e to the x over y minus 1 all over, okay, that's the left side, all over this junk. So e to the x over y squared minus 1 equals y prime. Wow. Well, it isn't that bad. I guess you could multiply by y squared on top and bottom. Here it is. You can multiply by y squared on top and bottom, and this will give you then y e to the x over y minus y squared over e to the x over y minus y squared as well. So it does, I don't know, simplify a little bit, but ugly, ugly, ugly. But yeah, I wanted to look at least an implicit differentiation one. So that's nastier than I thought. And then last one for differentiation. We're finding a tangent line here that passes to the point 0, 1. Okay. So what we have to do then is do the derivative of this guy to find our slope function. So it's going to be a product rule. So y prime is e to the 2x times 2 times cosine of pi x, okay, plus e to the 2x times negative sine pi x times pi, because that's going to be the derivative of cosine pi x, negative sine pi x times pi, because we did the chain rule for that. I don't really have to do much work. I'm just going to plug 0 in for x to find the slope, because remember this is this slope function now. So y equals e to the 2 times 0 times 2 times cosine of 0 pi plus e to the 2 times 0 times negative sine of 0 pi times pi. The nice thing is this is 1. 2 times cosine of 0, well that's just 2 times 1, because the cosine of 0 is 1. E to the 2 times 0 is again 1, but this is the really nice one. When I plug 0 in for that, sine of 0 pi is 0. So that cancels off. So we actually get our slope, y prime of 0, is 1 times 2 times 1, which is 2. So our line is y equals 2x plus b. Well, actually, they gave us the y-intercept here, plus 1. Okay. And let's take a look at that in the graph, because we can. F of x is e to the 2x times cosine of pi times x. Unknown command e. What? Let's do this real quick. F of x equals e to the 2 times x times cosine of pi times x. There we go. Whoa, look at that. That graph is insane. Oh man, that is nuts. They want us to find the tangent line at 0, 1. Well, I got y equals 2x plus 1. So let's see how that looks. Y equals 2x plus 1. Right there, nice and tangent. See what this guy looks like when I zoom out. Whoa. That's crazy. It oscillates, though, because of cosine. Going back and forth. So this, and then it gets huge because e to the 2x. That's an interesting graph. All right. So that's exponential derivatives.